Yeah,
So,
sounds good.
yeah, yeah. So very good evening to everyone. Uh, I am Subhomoy. A lot of you know me over here. So I am the co-founder and CEO of EduTime. I am an alumnus of IIT Kharagpur. And today we have with us a very good friend of mine from college, Vishal Singh. So Vishal, I remember back in college, while we were studying together, he had this knack for planetary sciences about astronomy and exploring how our moon evolved. So he went on to work with the Vikram Sarabhai Space Center in ISRO while we were in college, and then after finishing his bachelor's and master's in IIT Kharagpur, he went to US and he right now is working in a space observatory where he's working on icy moons. So I'm hoping that everybody over here will have a lot of learning, lot of inspiration from him. So I'll give the podium to you, Vishal. You can start off.
Thank you, Shubhamoy. And again, good evening, everyone. Thank you for joining us today. I'll get started. Okay, share sound. Okay, can you see my slides?
Yes, yes.
Okay, so I just have a summary slide or a initial slide at the beginning just to show you sort of some of the things that we'll be talking about. So just to give you some context about a few topics. So if you want to take a quick look, that's fine. Otherwise, I'll explain them as I go through the entire talk as well. Right. So, like I said, thank you for joining us on our journey to icy moons. I'm Vishaal Singh. I am currently a postdoc. I'm wrapping up my postdoc at Columbia University in New York. So I've been here for the last 3 odd years, and I've been in the US for the last 8 years, working on some of these things that Shubhamoy talked to you about. So I'm gonna start off today with a very brief introduction about who I am, what I do, how I got to where I am, and what I want to do next. And then I'll talk to you a little bit about what it means to be a geologist, and not just a geologist, but a scientist. You can change the discipline, but how do you actually get to be a geologist, and what is it does it mean to be a someone pursuing a master's degree or a PhD degree? And that includes the day-to-day aspects of that as well. And the second part, which I think will be more interesting to you, will be when we'll be looking at a lot of images and a lot of videos and sort of research we do in the outer solar system, as well as how do we actually go about designing a mission for space. So something like Chandrayaan 1, 2, 3, or something that NASA has been flying for a lot of years. But what I'll be talking about is much farther in space, like beyond Jupiter. So that's the basic structure of it. I can stop at the end of part one a little bit and take a couple of questions if that works, or we can take questions at the end as well, like whatever works. I want this to be interactive.
Yeah, so students, I think you can put in your questions as you get them in the chat. We'll be taking the questions once after the part one gets over, and then once part two gets over.
Sounds good. And again, welcome everyone. Excited to be here. So, for my journey, Bakshi or Shubhamay, sorry, I have mentioned a few things about what I was. So, I'm actually was born and raised in Jamshedpur or Tatanagar, which is around like 3 to 4 hours away from Calcutta, Kolkata. And as try to see if you can spot me in this image, but it sort of gives you an impression that I was not necessarily a very serious student when I was in school. But it was around 10th grade or so that I started actually preparing for JEE because at that point, like that is what we were told. Like you can either be an engineer or you go do AIPMT, be a doctor, or you join something like join commerce and pursue that. So at that point, I was like, my brother wants to be an engineer, so I'll be an engineer. And I prepared for JEE for 2 years, realized I was really bad at giving exams. So I messed up my first attempt. I got like something like 7,000, which I was like, I can do better. So I'm gonna go to Delhi, spend 1 more year learning how to like give JEE again, get a really good rank. And then I messed up my exam again. And I got 5,000 this time. And so it was the choice of like, do you do go to NIT and study mechanical engineering, or do you go to Kharagpur and study geology or earth sciences or chemistry? So it was more like science versus engineering at that point. And for some reason, and because my brother and I personally had been fascinated by movies and planetary science, so I was like, let's give geology a shot. So I went to Kharagpur to join the Department of Geology and Geophysics for a 5-year integrated MSc course. And that's where I met Subhomoy. You can see him in the hat on the image on top. And I was there for 5 years. I did an internship in the Indian Academy of Sciences. I was at ISRO for about 5 months. And so it was all it was an interesting period of our lives, but it was good to see what geology actually is and actually develop an interest in space exploration. After that, I moved to the US in 2016, joined Arizona State University for my PhD, and then worked for 3 years at the Jet Propulsion Laboratory at NASA. And for the last 3 years, like I said, I've been in New York working at Lamont Doherty's observatory. All of that to say that I am basically a planetary geologist. So, what is a geologist? A geologist traditionally is someone who studies rocks on Earth. They study how the rocks are made, what are they made up of, what are the processes involved in changing them over time, and how do we identify or detect them. By planetary geologist, I mean I work on rocks that are not necessarily on Earth, but on the moon or in space beyond the moon. So we don't have the ability to go collect samples to the field and just get it and bring it back to our office or our labs and study them. So we have to use a host of different techniques rather than field work to actually understand what a different planetary body is made up of. And that's some of the work I'll talk to you about today. Stack menu started. Can you see the audio? Yeah. So,
Eagle Eye, you remain
let us
strong.
play for a second. Touchdown confirmed. We're safe on Yeah, so this was back in 2012, and if some of you may know this, this is the landing of the Curiosity rover that NASA sent on Mars. And so this is some part of it is a simulation of what actually happened, and the rest is this actual video of the team inside the JPL mission center, looking at detecting how the mission is going, and actually when they got confirmation that it landed. So I used this video because this is exactly around the time I actually got involved in research. So around 12 years ago, in my second year at IIT, I started I wanted to seriously pursue planetary science, and stuff like this was happening. But that was the first time I actually picked up a book on planetary science. I mean, I had studied all of the coursework for geology, but I wanted to learn more about what is happening in these worlds. And so I started reading books about it. And so it's you, I only had an interest at this point. I didn't have as much knowledge, but that's sort of what you need. But my inspiration for most of this work has always been movies. I grew up watching movies and I wanted to do what they were doing in these movies. And that's sort of again, how I got into it. So what I'm going to talk to you about first is the moon. And these are actually images from the Apollo 11 mission when when the astronauts went to the moon and they collected samples. So I had said we don't have samples for most planetary missions, but we do have samples for the moon. We actually have around 382 kg of samples, and most of those are these massive rocks. And to put it in context, it's like the amount of weight you can put in a small car. Like 5 people, 6 people sitting in a car is the amount of weight that we have for pretty much all planetary samples in our entire solar system. And the best part about this was so when they were actually collecting samples and Neil Armstrong was bringing back samples from the moon, so they had these boxes and they had these massive boulders. So they had extra space. So he just picked up a lot of the moon dust and put it inside just to fill it up and pack it properly, sort of like how they would do. And most of the real science came from that moon dust because all of the others were one type of rock. Everything else that came was grinded up and different mixtures. So that's sort of how we actually know what is on the moon, what is it made up of, how old it is. And my first project was looking at images of the moon and trying to figure out what are the different features. Like, is this a mountain or a valley? Is this a crater? And I actually have a couple of links here that I'll email to the editing team as well. Just to, if this is something of interest to you, you can actually go on the internet and look at any images of any region on the moon at whatever resolution you want. So as small as like 10 meter per pixel, you can go look at that. And if you want to contribute, there's a citizen science program as well. So you don't have to wait to be a scientist. You can start contributing to research today. So I'll send these to you if you're interested. But I want to give you some examples of the images that we have from the moon. Does anyone know what this is an image of? Any guesses in the chat? Okay, I'll tell you. This was the Chandrayaan-3 landing site for the rover, and then the subsequent module that we just got earlier last year. Then these are some other images of the moon, and these are of the order of kilometers wide. So you can see these massive holes, which we call impact craters. So on the left-hand side, you have one crater that is superimposed on two other craters. And on the right-hand side, you see a landing site for a future mission that NASA wants to send. So that's an Artemis mission. And so as you can see, the moon looks to be pretty much dead. There's not a lot happening on it. There's no vegetation, no plants, no atmosphere pretty much. It's a very thin atmosphere. So all of this is, but it still is a like great target for interest because a lot of the stuff happening on Earth is also happening on the moon, and that is what we were trying to understand. So we take something like an atlas of the moon, and then we start mapping features on it. And this is a career in itself. People spend their entire lives just looking at images of planetary objects and mapping them to see like, is this a valley? Is this a crater? Is this a mountain? Is this a gully? So anything that we find on Earth, you can pretty much find on the moon. And so this was my work because I didn't really know a lot about it. But the professional standard is this. So if you add some more color to it, if you add each color represents a specific type of soil or a specific type of rock. And so this is sort of like a geologic map of the moon, where you can look at this and you can figure out which region is how old and what is it made up of. After that, I went to ISRO for a bit, where I worked with one of the heads of a SARA instrument on Chandrayaan-1. So they were looking at how the particles from the sun interact with the moon. And so the map on top is sort of like a reflection of how much of the solar wind is going to the surface and how much is coming back. If it's green, more of it is coming back. If it's blue, less of it is coming back. And so they were looking at the properties of the moon to see why is it low in some parts. And so they found there was like a magnetic field of the moon that was stopping it from doing it. And then there was another project where I was working at Arizona State, which is again looking at if you don't have good images, how much data can you get? But to broadly summarize what I do, so I try to study the moon and these other worlds in the outer solar system at different scales of exploration. So I use data from flyby or orbiter missions where a spacecraft goes around an object, or it lands on the surface, or it goes into the ocean or underneath the surface. And we look at data from all of these different types of missions and try to understand what is the planetary body made up of. And I'm not going to get into a lot of detail, but like each of these is like a different technique, and that allows you to like models, maps, spectroscopy, different missions. And so all of that is basically techniques that you use to study not just our moon and Earth, but also objects in the outer solar system. So how do you become a geologist? And this is not an exhaustive list, but this is just to give you an idea of like the steps involved in any sort of such a career. By the way, what's the time? Like, how am I doing on time?
It's
Right.
okay.
Okay. All right. So yeah. So the first thing that you need is an interest. That is it. Like you don't have to have any knowledge about anything. And again, this is relevant for any field. The second and third are interchangeable, but all of you are gonna go ahead and most of you are gonna pursue a undergraduate degree. You're gonna get your bachelor's in whatever field that is of interest to you, and then you can do projects and internships while you're there that get you an interest in whatever field you want to be involved in. If you want to do geology, there's a whole lot of different tags. It can be earth science, it can be environmental science, where you want to study climate change. How does the carbon dioxide in the atmosphere change? If you want to study about planets like Moon or Mars, then you study planetary science, or it can just be called geology, geophysics, climate school. It can be any names. Another way to get involved is still pursue engineering, which is like if you're interested in being an engineer, then you can be an engineer, but there's an opportunity to get involved in these space missions as an engineer. So a lot of people working on these missions have to actually design these components. They have to design the rocket, they have to design the spacecraft. And so those are engineers. You can also do a lot of different sciences. You can do data science, physics, chemistry, and all of these are people involved in these missions. So it's like just if you're interested in something, go pursue that. And if you want to get involved in space missions, there is a way to do that. After undergrad, most of us choose a job in the industry. And if you want to be a industry geologist, then you can work in oil and gas, something like Coal India, ONGC, Schlumberger. Or if you can go work on the environmental geology, you can work for the government, and as well as like keep learning about it. On the other hand, with if you don't want to do like a 9 to 5 job as much, and you want some more flexibility in the sort of projects you want to do, you choose the path which pays you less money, which is going for a master's or a PhD program. And again, if you're doing a PhD in geology, you can be writing code to make models. You can be trying to recreate everything that is happening outside in your lab. You can actually be going out into the field, or you can be working on missions or spaceflight. If you do all of that, so I also at any point you can join the industry. The more qualified you are in the sense of degrees, then the more money you make in the industry. So that's always an option. But then, like this is what I was doing. So I became a postdoc after that, which is a postdoctoral research scientist. And here you get like actually have freedom. You choose your own projects. You choose where you work. You choose how much time you devote to each project, and you're working on multiple projects. So you're almost a scientist, but they won't want to give you that much independence yet. And then you become you either choose a career in research where you become a research scientist, or you choose a career in academia where you teach students and you teach others how to be a geologist while also doing research. The good part of academia and professorship is they pay your salary for 9 months a year, but in research, you have to write grants and scholarships and apply for all of those to get the money to fund your research and your project. So that's the difference. You have all of your time to yourself, but in professorship, you have some time to do your research. And some of us who are really lucky and really good at their jobs can choose to become an astronaut from that. So there's an astronaut application programs where you can apply to as a postdoc. And if you go through multiple rounds of selections, and if you can make it through, then you can join NASA or you can become an Indian space astronaut and just have that life for yourself. But yeah, that's sort of like just a brief overview of, again, this is not exhaustive, but just to give you a sense of what it is like to, like, how do you actually go from having an interest in something in high school to actually getting to somewhere where they give you a job as a scientist. Right. And yeah, again, if you have questions later, just put them in the chat. We can talk about it. And where do you do this? So in India, we are lucky to have a lot of really, really good institutions. So in the university level, we have IITs, NITs, IISc in Bangalore, IISc, Indian Institute of Space Science Technology. And then you actually also have ISRO where you can do internships. So Bakshi mentioned the Vikram Sarabhai Space Center. We have the Physics Research Lab and the Space Application Center in Ahmedabad, and NGRI is in Hyderabad. So these are all like excellent opportunities where there's always looking for students who want to contribute and just like spend a few months of your summer or your winter just doing an internship. And that allows you to actually work for it on your own. You figure out if this is something you want to do and then pursue it further. In the US and Europe and Japan, they all have a lot of really good universities and they all have their own space programs. So you have NASA, you have the European Space Agency, which is in Switzerland, Germany, France, Spain. So if you want to travel the world while you're studying, you can go do that. And Europe has a 3-year PhD program. So you actually get a PhD earlier than the US, which is anywhere from 4, 5, or 6 years. So, like, if you want to travel, go do that. And you have UAE, China, Russia. So, like, if you want to get involved, there's definitely lot of different places you can go. But like I said, India has a lot of good opportunities as well, but not a lot of money. So, what is a PhD? And this is something that I did not know even when I was doing a PhD. So, I want to actually use a graphic or a comic that I really liked, and I hope you enjoy it as well. So, if you imagine a circle that is all of human knowledge and everything that we know about universe, about matter, about politics, everything, every single subject. So when you finish like elementary school, like second grade, third grade, you know a little bit about it, what your parents have taught you, what schools have taught you. When you get to high school, you start learning a little bit more. And this is the, sort of the stage that where you all are at, where you know a lot about a lot of different things and you have a more comprehensive knowledge. When you go for your undergraduate degree, your knowledge about everything will again increase, but you'll also gain a specialty. It can be something like mechanical engineering, or it can be geology, or it can be something else. So you know, and obviously this is not to scale, like the knowledge can be a lot more than this. I'm just showing this as an example. But yeah, you gain a specialty, but you also gain an understanding of everything else. Then when you go for a master's degree, you can either choose to deepen your knowledge in that one specialty where you did your bachelor's, in which case your arrow will grow in that direction, or you can go do something completely different. Like you can be a mechanical engineer for your bachelor's, for your master's, you go data science. And so your arrow will now point in two different directions. And so you have two different things that you have a specialty in and different levels of knowledge. The more you read, be it research papers, newspapers, you look at stuff online, you read articles, you see the news, then you'll sort of get to know what is the edge of our human knowledge, like what is the best that is happening in space right now, what are we exploring. But when you're doing a PhD, that is that one small single boundary that you're focusing on. You actually don't know anything about the rest of human knowledge. You have that one special specialty, and you spend 3 to 5 years just working on that one single thing. So if you zoom in on that, so you spend years working, just pushing at that small boundary, trying to see, okay, can I do this? Does that expand my knowledge? No. So I failed on that. Let's do something else. Let's approach a different way. And just learning. And then after years, that boundary starts giving way. And so you have a little bit of a dent that you've made, and that is your PhD. So you think that, oh my God, I have changed the world, and this is all of this new knowledge that you've done. But if you look at it in the bigger picture, that small speck on that circle is everything that you've done. So it's like, it's not the end of human knowledge, or it's not an exceptional feat. It is certainly a great feat that you got a PhD, but you have you're making your own small bucket in the ocean. Like you're just adding a drop in the ocean. So you have to keep working at it. And if this is something you really enjoy doing and you're really passionate about, then I definitely recommend you getting a PhD and spending those years. But it's also, like I said, with a bachelor's degree, with a master's degree, it's all about your interest. If you want to learn more about our universe and what we know, then that's also good. Like whatever works for you is good for you. Not everyone has to do a PhD, but if you do it, you can make a dent, and then you can spend the rest of your career keep making dents as much as you want, and that'll be a really good career and something that can maybe one day lead to the whole of the circle expanding. But an expert in a PhD is only an expert in one small field. You don't know anything, or you know very little about everything else that is happening. So I'm not an expert in civil engineering. I know next to nothing about it, apart from like what we learned in bachelor's degrees. So just to give you some context, if this is something you want to pursue, then I definitely recommend it. It's very enjoyable, but the day to day is not you making exceptional science discoveries and doing so many fascinating things. Most of the time, you're writing for at least a month or 2 months in your year because, like I said, you're applying for grants. When you find some new research, you're writing papers to publish it and communicate it to everyone. You're writing reports to communicate it to your grant funding organizations like NASA in our case, where we're trying to tell them this is what we've done for the last 6 years. And then you're also going to conferences and presenting to people like, hey, look at our work and networking, like building connections with other people in your community who are doing that. The rest of the time, though, you do get to do a lot of fun things. So you get to build your own machines, you get to build your own instruments, you get to cut things, break things, and just enjoy working in the lab, which is something I do. Or you write code. You can spend years working on your models, trying to get as much information as we can from your model predictions as you see on the real world. And then for some of us, we love working in the laboratory. So for that research aspect, we build instruments and then we collect data from instruments to perform the real science. So science is 3 quarters of a year of what you do. The rest of it you spend doing the unglamorous stuff, which is writing. So again, you have to be passionate about something that you want to do. But if you enjoy doing it, then I strongly recommend it. Okay, so that is sort of part one. I do want to finish with this, and some of us were really lucky and like we're really passionate about it. You do get to go out into the field and actually do field work. Uh, so this is an example of an ice penetrating robot here on Earth, which is something that we're going to be talking about ice penetrating robots on Europa and other icy worlds later. So you can actually go out onto Antarctica if you want, spend months there and test your robots there. So there's a lot of fun things to love about the job, but there's also the reality of it. So I just wanted to present both of those aspects to you before we actually get into all of the science and the fun images in part two. So if you have any questions, I can take them now. Otherwise, we can proceed to part two.
Yeah, so there are some questions that I've noted down that were asked by students. So I'll
Hmm.
just read them out to you.
Sure.
So the first question was from Aditya. He asked that, is it true that we can put something in moon's orbit just by throwing it very hard?
I would say probably not. You'll have to throw very, very hard and very, very close to it because the moons. So when we put something in orbit, it's because of gravity, right? So the gravity is holding it in its orbit and making sure it's moving around it. So it has to be within the gravity range of the moon, within its gravitational attraction pull, and it has to be very strongly foreign. So, like when we actually send missions to the moon, something like, or even missions to the outer solar system, we do use the moon's gravity pull. So we throw the spacecraft at the moon very, very hard with rockets. It goes on the moon. It uses the moon's orbit to slingshot. So it gains speed and it slingshots around it. And then they have to, but if you don't use rockets again, you can never leave. So you just keep going around and around. So then they use rockets again and actually leave orbit. So yes, you can't get something in the moon's orbit if you throw it hard enough, but it's hundreds of kilometers per second or something like that.
Yeah, so I'll add on to it. So there is something called escape velocity. If you want to
Yes.
escape Earth's gravity and go on our orbits around 11 kilometers per second, that's how hard you need to throw. In moon, it's 2.4 kilometers per second. So it's not that easy.
Yeah.
It's
Yeah.
yeah. So the second question that he had asked was, is it true that moon is a part of Theia?
Yeah. So Theia, I assume, is what you're saying is the original, like the parent Earth. So basically, yeah. So that is the leading theory that the moon was a part of Theia, and then there was an impact, sort of like the sort of impact craters that I was showing earlier on the moon, but a much larger scale impact, sort of the order of like what killed the dinosaurs here in on Earth, but much before that, much before any of that happened. And so we do think that there was an impact, and then a lot of the rock and materials from it and gases were from Earth was from proto-Earth as we call it was ejected out, and then because of gravity, it kept like crashing against each other and then became the moon, and that moon kept moving around the orbit. So yeah, it is. I would say it is there.
Uh, right. So that then there is a question that two students have asked. One is Anchita and one more Aditya again. So they're asking, can we colonize Mars? And then Aditya added on, by heating it to generate oxygen from its oxide present in its soil.
Yeah, so you need a lot of heat again. So like one of the ideas that like Elon Musk was doing the SpaceX stuff was thinking was like putting nuclear bombs on the poles. So that is the order of heat you need to actually heat it up. So the much easier idea that people want to do is like the moon is closer, moon has water on it. That water you can use to create fuel to go out into the Earth solar system. So why not colonize or rather set up a base on moon first? Have something again. You don't have an atmosphere, so you're gonna have to figure out a way to make an atmosphere. You have everything sealed, but actually set up something there. Take out some materials from the moon, and then think about colonizing Mars or anything beyond. So maybe in after all of us are dead, but I won't say any time in the very recent, at least not in my lifetime. I don't see it happening. But we have good films and TV shows we can see to think what that would be like. So I
We'll be
recommend doing
those
that.
shows that we see.
Yeah.
Mhm. So
Yeah.
the
So
next
I,
question was from Amol Dalmia.
yeah.
He was asking that should we direct our science R&D towards a space when people in Earth are dying of hunger and war?
Yeah. So great question. There was actually a nun who had sent this very same question, and like wrote a letter to the president, I think, of USA a long time back, or I think the president of NASA. I don't remember. Just exactly like what is the actual value that space brings to exploration or like or to Earth. And this, I actually have two slides about this at the very end of my talk. So if you
Okay.
can wait until the end of part two, I'll talk to you about like what is the impact of planetary science and why do we actually do it. And if you're still not convinced, then I'll try to convince you.
All right. So the next question is from Bhavanshu Maharaj. He's asking, did you complete your project on ice
Yeah, so I,
penetration?
yeah, so I'll actually be talking about that in part two. So we have completed our project, but that is just part one of three parts before you actually even think about. So before we send anything to anybody, we have to actually qualify it and make sure it works under those conditions. So we've been doing a lot of that in the laboratory, which I'll talk about. We have to now actually go out into Earth's like ice fields, like Antarctica, Greenland, and make sure all of that works there. So that is the next few years. And then after that, if we are very lucky and everyone wants to do the same thing, like maybe 10 years from now, we'll actually try like building those missions and sending that. So this is like that is a whole talk in itself. Like how do you actually get a mission funded? Because everyone has their favorite object and everyone wants to go there. So you have to make a very strong case why my favorite object is the best object. And so that takes time, but yeah, there's a lot of good missions that are going to happen.
Hmm. All right. So one more. There are three more questions. So one is from Mohammad Rasab Adil Ansari. He's
Mhm.
asking, what is the moon really shaped like?
Sort of like a sphere. So it's like because of, like I said, because of gravity, both the moon's internal gravity and the Earth's gravity, it's sort of like it wants everything wants to like pull itself together as almost like a sphere or a circle, right? So it's like because everything is because of gravity is pulling towards each other, it ends up like becoming very uniform throughout. But there are a lot of variations in topography. So if you look at the actual surface, you can get like kilometer high mountains, lots of craters, which you don't see as much on Earth because like we have like water and erosion and wind, and that takes everything away. And like we have jungles, which hides any variation that we see. On the moon, you don't have houses, so you can see where it's going up, where it's going down, where there's a gap. So yeah, I mean, but it's mostly spherical, I'd say. Like there's a you can find the radius and yeah,
Hmm.
that's it.
Okay. So Anurag is, nee, sorry, Amol is again asking, I read your article on signals through the ice world. How did you
Hmm.
think of this? I think we'll be covering that in the next part.
Yeah. What was the question? Uh,
He read your article on signals through the ice world. So,
yeah. Yeah. Okay.
uh, very
Yeah, I'll talk about that in the next part of the thing. So yeah, thank you for your question. I'll do that. Okay.
okay. So, were you interested in Star Wars? Fan Mundal is asking.
Yeah, I was. reasonably interested in Star Wars. I did not. I watched the prequels before the original movie, so I have seen that. But like I said, I love Armageddon, which is not a really good space movie. Like it's very inaccurate, but it's like good to see what we think space exploration is like. Like we can send oil drillers and have them drill and become astronauts. I wanted to be an astronaut, so I was like, yeah, I can do it.
All right. I think we can move on to the next part.
Yeah,
Students, if
and I
you have any
saw one
questions,
more
I'll keep
question
noting
from
them.
Aditya about Europa Clipper, I think. So
Yeah.
Clipper is a mission that will launch in October, I think 10th October 2024. I'll get to the questions after the second part. Thank you again. All right. So I'm gonna go on to the science, or more of the science part of it, and show you lots of images, some videos. Again, put your questions in the chat. So the second part was like most of my research over the last 6 or 7 years, where we are trying to, like geologists do here on Earth, where they try to unravel the story of rocks. So I've been studying ices in the outer solar system and been trying to unravel the story of ice. How is it made? What is the context in which it is found? And how do we detect it? As well as the oceans. Yeah. So, so I'm actually going to start off with a clip from a movie which talks about solar system evolution.
Let there be light. And light was. And it was good. The first day. And then the formless light began to take on substance and shape. The second day. And our world was born. Our beautiful, fragile home. And a great warming light nurtured its days. And a lesser light ruled the nights. And there was evening and morning. Another.
So that was actually a clip from a movie called Noah that was released in 2014. And if you want to see the entire clip, it's like 4 minutes long about how Earth evolved. And it's like reasonably scientifically accurate, but it's just like it's a good visual to have of like how our solar system was formed, not the universe in general, but our solar system. So you see this initial like blast of light in the beginning, which is like the death of a star that existed previously, creates all of this like a disk of debris and matter. Hold on. Yeah, so it creates this debris of rocks, dust, ice, matter, and then you end up all of it exists in a disk. You have an initial sun, which is what we call a protosun, and this disk inside of it, around of it. And all of this because of gravity and because of collisions. So like you have all of these different rocks which you saw was colliding against each other, and that starts leading to this creation of planets. We call this accretion. So having, because of one rock collides against the other, some of it sticks together, that becomes heavier than all of the other rocks around. So that pulls on other rocks because of its gravity. And different parts of the solar system had these rocks forming, and they grew larger and larger. They pulled gases, they pulled ice, they pulled rocks, and that led to the creation of planets and what we see as the solar system. And you might have actually also seen the formation of the Earth at the very end and the formation of the moon. So there was an impact on the Earth, and they visualized what it would have been like for like all of that material to come out of Earth and actually create the moon. So that sort of led us to the solar system as we know it today. And this is a chart that we've seen in all our science classes and growing up. And this is almost to scale, where you have the sun on the left, then Mercury, Venus, Earth, Mars. Then you have these massive giant planets and gas planets, which is Jupiter and Saturn. And then outside you have Uranus and Neptune. One thing I wanted to point to towards is this red line, which we call the snow line. So sort of like the same thing on Earth, where we have a snow line above which snow can exist in on Earth, like on mountains. So like if you go from Kolkata to Darjeeling or Missouri, you're going higher, and the air is getting thinner and it's getting colder, and you start seeing snow. So the same concept is applicable in our solar system. As you go further away from the sun, there comes a point right before Jupiter where it's cold enough that the water that you exists as liquid here on Earth exists as a solid, as ice in the outer solar system. So anywhere on the surfaces of these worlds, you can actually get like crystals of ice. So sort of like ice cubes in your freezer. So that's happening in the outer solar system. And if you see that yellow line before Saturn, that means all of the carbon dioxide that you exhale, that now exists as ice as well. You go further out, you get lots of different organics, ethanol, methanol, ammonia, all of these are ice. So what we think of as rocks here on Earth, these ices behave like those rocks in the outer solar system because it is so cold. So like conditions around Jupiter are close to minus 200 degrees Celsius on the surface. So that is exceptionally cold. And that is why the ice is, all of this exists as ice. Now, I want to talk to you a little bit about the Jupiter system and focus on that. And I want to bring it back to our like Earth first. So we've all looked up at the night sky at some point in our lives and wondered like what's out there, like what is going on in the universe? Is there life elsewhere in the solar system? And that is sort of the same question which like almost 400 years ago motivated Galileo to discover the moons of Jupiter. So Jupiter right now has something like 80 odd moons, but he was like the first one to discover the four major moons of Jupiter. And you can see that with those star and asterisk marks on his piece of paper from the 1610. But cut to present day, they're like no longer scribbles on a piece of paper. We have real data and images. So we sent missions to the Jupiter system in 1990s, which were able to go around these bodies and we were actually able to see what they look like. And what we found was that Earth is not the only ocean world that exists in our solar system. So, and by an ocean world, I mean something that has a liquid body of water, either on its surface or its interior. And so, what we found is that if you look at Jupiter's moons, Europa, Ganymede, Callisto, we think they have liquid water in its interior. So, not on the surface. The surface is covered with ice, but like here on Earth, you have a crust, which is all of the soil and the rocks on there. Then you have a mantle, and then you have a core. Here you have on Jupiter's moons, you get an icy crust outside. Then you have an ocean of hundreds of kilometers. And then you have your mantle, and then you have your core. So the life originated here on Earth in the ocean. So they think that if life exists on the oceans of Earth, why not in the oceans of these other moons, which have conditions similar to it? So this is one of those moons, and the moon that I've been spending a lot of time working on. This is Jupiter's moon Europa, and its surface is covered with ice, pure water ice. So similar to the ice, like you said, you have in your freezer, but not necessarily. It's very cold. It has its properties are very different. It's almost as hard as granite because of how cold it is. And all of the orange stuff that you see is actually salt that has undergone radiation. So, like if you go to get your X-ray, you get a little amount of radiation, like multiply by that by thousands of times, and then you get some regular white salt turning orange and red. And we actually see something similar to this in Antarctica, where there's some salt that has changed the color to become orange, and we find some like microbes and life in Antarctica around that. So they're like the surface looks really interesting, and there's an ocean underneath. So what is going on here? And so Europa Clipper that I was mentioning earlier is actually going to go here in 2024 in October. It's going to fly in 2024, take 7 years to get here. And by 2031, when you guys are graduating your bachelor's degrees and getting ready to like figure out, like, hey, I want to be a geologist or like an engineer, then you can actually, you'll have data from this and you'll be able to see what these moons look like at a much higher resolution. And this is just an image of some of the weird things that exist on these moons. So you have all of these crisscrossing bands, which is actually like tectonics, like earthquake-like events happening on these worlds, where the surface is squished and then it's stretched out. So you get like these small column-like bands on the leftmost, which is like crisscrossing each other because like multiple stages of squishing, stretching, squishing, stretching. And like there's a lot happening in the interior. In the rightmost, you see like these craters again, like similar to Earth. And you see something like these. If you look at Earth's mountains from top, or if you go on Google Maps and look at this, then you'll actually have like see something similar to this on Earth, which is like the peaks of mountains. So there's a lot of like really fascinating things happening in these worlds, which you want to know more. If you go further out in the solar system to Saturn's moons, this is Enceladus. And Enceladus is mostly made up of ammonia ice. So again, it's all a lot of water ice and ammonia ice. And so it looks very white and bluish. And it actually has something which is very fascinating. It has geysers on its surface. So it's throwing out water outside of its surface from like interior ocean. It's connected to that. It's coming out. And like if you go to any of these hot springs or geysers here on Earth, like it's doing the same thing, but kilometers of like a waterfall that's going out into space. And so this is a real image from a Cassini mission, which captured these geysers. And we think something similar is happening on Europa as well. So like you can see why even if there was no life, you would want to see what the hell is going on here. Like what are they doing? How is this happening? And so I don't have a lot of text in my slides in general, but I have some here. You don't have to read all of it, but this is just to show like as we go outside from Jupiter towards the outer solar system, you can see how each moon has its different ice. You see a lot of H2O, which is water ice. You see a lot of carbon dioxide, which is CO2, which is carbon dioxide ice. You see some in Neptune and outside you see a lot of organics. So these are things that you'll learn a lot more about and you're already studying. But as that snow line is shifting for different materials because it's getting colder and colder further away, you get lots of these different ices. And these are all like detections we have and data we have. So we have an understanding of what is out there, but we don't have samples for any of them. And if you look at our predictions for the internal structure, again, so we think all of these have like ice shells outside. So like ice that is frozen of the order of kilometers. So not just like on our glaciers here or like a few centimeters of snowfall. It's like 7 to 10, 25 kilometers on Europa, just like the entire surface is hard ice. And Enceladus, it can be as much as say 30 to 40 kilometers. And then they have hundreds of kilometers of oceans underneath it. And I've shown you some of the temperatures here as well, but it's just to say that it is very, very cold. And it is a lot different than what we think of ice when we think of ice here on Earth. And that is what we have to recreate because we don't have samples. We have to recreate this in the laboratory. We have to make ice that is that cold and stays that cold to see how it behaves. And I wanted to show you something of like the amount of research that is being done for planetary science. So this is a fleet of all of the different satellites and missions that has flown from NASA on Earth, around the sun, around the moon, around Mars, Jupiter, Saturn. So you see there's a lot of stuff happening, especially on Earth, but also now we're going to get a lot more in the outer solar system. And ISRO is catching up as well. So we already have 123 plus missions for ISRO. Most of those are around Earth, but we do have some missions like the Chandrayaan 1, 2, and 3, and the Mangalyans, which is the Mars missions that we have here on Earth. So India is like this planetary science is a great target or like a source of interest for India. And you've seen all of the news and Modi ji and everything are talking on the news about it. So this is something that is going to be around for a while. And this is an example of one of these missions. This is Europa Clipper that I was talking to you about earlier, which is if you just Google Europa Clipper, you'll get a lot of information about what are the instruments on it, when it is flying, how is it going there. But this is actually going to do flybys of Europa, and it's actually going to get us data of real images, images of how data about how light interacts with the surface, and get us information about what is the surface made of, how old is it, what is the internal structure, like how thick is the ice, is there an ocean underneath? So confirm all of those. And this is a video of what it would be like for a Europa Clipper mission to fly. So you can see Jupiter initially, and it's in orbit around Jupiter actually. And then you have Europa Clipper, which is approaching Europa. and it's going to do 40 flybys. So 40 times over a period of a couple of years, it's going to fly by Europa at different orbit kilometers, distances from Europa, and that will give us an understanding of like what is this made up of. Right. So, like I said, the goal is the same as what Earth geologists do. We want to understand how the rocks are made, where are they found, what is the context, what are the different processes by which they are changed, and how do we detect them. And that is work that we've been focusing on, and I've been focusing on for the past few years, where what we're trying to do is study all of the different processes that are happening on Europa's surface. Like there's radiation, there's some liquid water coming from the bottom, there's some impact impacts happening like meteorites and everything else. And we're trying to see sort of like Armageddon, just like drill through it and figure out like what is happening in the subsurface. What is the surface made of? Like, is there like if you see all of those bands and the squishing and stretching, like how was any of that made? So just trying to understand not just the surface property, but the subsurface property. And how do we do that? We run experiments. I mean, like I said, there's a lot of different things you can do. For my part, what I was doing was running experiments. So there was an eye spectroscopy lab at JPL where I was working for approximately 3 years during my PhD, and where we have all of that stainless steel equipment and copper that you see on the sides. That is all equipment that we use to get to minus 200 degrees Celsius in our laboratories and to make ice samples which are the same as the samples we expect on Europa or Enceladus. So we are able to recreate that with the same composition, the same properties, like what is the size of the grains, or how strong is it, how does it behave, and do all of that in the laboratory. So how do we do that? So first, we make samples at minus 200 degrees Celsius. So we use liquid nitrogen, which if you put your finger in it, it's going to immediately start like doing a few things that you would not enjoy, but it's kind of like it's very cold. But we use that, and we use something like this sort of setup where we can make samples of different grain sizes as small as like a few microns, and then we can sieve it to get the size ranges that we want for the surface. And then we use that, and we get different crystal structures as well. So like ice, depending on when you freeze it, like in our freezers, when you freeze ice at like minus 20, minus 50, it's like mostly crystalline ice. That's one form where everything is in structure and ordered and has a good geometry. If you freeze it at minus 200, then it's amorphous ice. So it's just like something like flash freezing something. You just put something in really cold stuff and it just immediately froze. So that's like very disordered. So we try to recreate all of that in the lab. And then we use something called spectroscopy. Now, spectroscopy, what it is it is studying how light interacts with a surface. So you have light coming from the sun. It approaches something like the surface of the moon at an angle, and then it gets reflected back at an angle. And again, this is like geometry, and we are all familiar with this. So what the spacecraft does is it measures the light reflecting off of the surface, and that data tells us what the surface is made up of. So it's like a different wavelengths of light. You get different absorptions based on the material, and that is just the simple concept of spectroscopy and what we use in the lab. So we recreate that process in the lab with lots of different equipment. You don't have to like read it, but like we have our samples. We use microscopes to look at the samples, and we use spectroscopy. Different ways of doing it, but we have these two different setups, and you can see lots of wires, lots of stainless steel equipment. So this is all in vacuum. So we are able to actually get rid of any atmosphere around our samples. We can actually have a gun that shoots electrons. So you can radiate your samples. So we're doing as much as we can to simulate what it is like on Europa. And we collect the light reflected off our sample in that small orange copper sample holder. So like a few millimeters and centimeters of ice. And that recreates everything we know about Europa. Then we do a lot of other stuff. We can go out and like have like really high radiation. So like all of these equipment is to replicate what is happening on Europa. We take salt and we send these electrons on it, and we recreate the orange stuff that we were seeing on Europa in the lab. Then we look at, so you can see the fumes coming off of the ice. So this is ice at 100 Kelvin. And you can see what the scientist here is doing is she's measuring the hardness of ice. And that is how we found out that it's like as hard as granite. And then you also use the microscope to look at the different properties. So again, we're trying to just recreate as much as we can about what we know about the surface. We look at the geysers. We have equipment in the lab that can actually create geysers. And we see how is it happening, what is happening in the interior. We look at how the surface is changing with the sun. So if you put ice underneath the sun, it starts melting. But if it's at 100 Kelvin and it's very slow sun, like very low intensity of the sun, then what is happening to the ice? So all of that, and then we use like wax and sand to create that squishing and stretching I was talking to you about. So like everything that you can imagine, people are trying to replicate that in the lab. Because again, we can't go there. And then using sort of like that light that is reflected off of the surface, we are able to measure different parts of it at different wavelengths. And that gives us if it's like a different type of ice. So again, like lots of equations, a lot of stuff, we don't have to get into it, but it's like this is the basic concept of spectroscopy and recreating what you see out there in the lab. And that gives you what you get. So you start off with what you know about the surface, and then you can actually get estimates of the age. How old is the surface? What is it made up of? What is its crystal structure? So all of that is done in the laboratory. So that is one part of it. I want to talk to you about the more fun, more less sciencey, but more mission design part of it, like the ice penetrating robot. And this is talking about our journey to explore through the ice and into the interior oceans underneath these ices. So right now we've been studying the surface. Now we're going to study what lies underneath the ice in the subsurface. So again, this was a project looking at beyond flybys or orbiters or landers. We want to actually go in the interior and send robots which can melt through the ice like this image here and go to the interior. Now, the concept or the goal of this work is the same. Like we want to search for life that exists underneath the ice. And this is something we've been doing here on Earth for like ages. We have these ice chisels and lances where like anywhere it's cold enough, you would make a hole in the ice and do ice fishing. And that's what we're doing here. We're fishing for life with these really state-of-the-art equipment. So the image on the right is like the latest iteration of what a robot looks like when it's actually going through the ice. So we have something like a drill at the bottom and some water, like hot water that is melting the ice. And because it's so cold, the water starts immediately freezing around it. So we have to figure out a way to deal with all of that. And so one of those is this robots which are used here on Earth. So this is a robot that is actually melting 100 feet into the glacier. So I'll just play that again. But you can sort of see the melting around it, where it's like penetrating through the ice and then it gets to an ocean part of it. And then what we want to do is once you send your robot in the ocean, you want to be able to communicate with it. Like, how do you actually get data back from your robot, which is stuck 10 kilometers below to the surface? So we're going to use a concept which is used here on Earth, fiber optic cables. So you can see all of the fiber optic cables that exist here on Earth in the oceans. And to give you some context, fiber optic cables are what we use to get internet, what we use to get mobile networks, what we use to get like transfer signal immediately from one part of the world to a different part of the world. And all of that is happening because we have these fiber optic cables that are laid down all across the world. It was started like doing in the 60s or the 70s or something like that, and it has been around forever. And that is how like we are able to talk to each other today. So we are using the same concept, these fiber optic cables with our robots. And what we're trying to do is design a mission that can actually, and this is just an artistic conception, but design a mission that will land on the surface of Europa melt through all of the ice, get to the ocean, and then have this fiber optic cable behind it that is communicating with a lander on the surface. So that is sort of like the basic concept of the mission. But the challenge is that there are a lot of different ways by which your mission can go wrong. So you have something like you're starting off in vacuum at the surface, then you're melting through kilometers of ice. You have different like cracking, you have lakes inside, you have salt, you have sulfuric acid. So if you've ever been around sulfuric acid, then you know it's incredibly dangerous and you don't want to touch it. But our robot has to actually go through it and drill through ice that is filled with sulfuric acid. And then you also have earthquakes, or like in this case, ice quakes happening in the interior. So you have to survive all of these conditions. And then you have to survive the temperature. You start off at 100 Kelvin or like minus 200 degrees Celsius. So all of that has to be navigated. And how do we do that? Again, laboratory experiments in the first step, which is what the paper was about. Then we combine it with our robots to see how all of it is working together. And then finally, we go out into the field. And this means like going out into the field in Antarctica or somewhere else and testing out everything together to see it works. And then you want to go out to space. And again, these are missions that are planned 2 decades in advance. So we're at least like 10, 15 years before any mission can actually fly. So how do we do that? So I've been working during my postdoc at Columbia University, and we have a ton of different equipment like chambers that go down to minus 200 Celsius, which is this blue chamber here on the left. You have walk-in freezers, which is like minus 25, minus 30 degrees Celsius, where like we suit up, wear lots of jackets and make samples inside. And then we recreate like what the seismic environment is like, what are the ice quakes happening in these different equipment up top. And that allows us to not only recreate the surface, but also the different samples. So how do you test it? First, you have probes that are going through the ice. So this is a lab example of one of those probes or a smaller version of that probe that is drilling through pure water ice. So you can see that slowly making its way down through it. What we do in our lab has been making these samples, looking at these fiber optic tethers and making foot-long samples of ices with these pre-existing locations where it can fail. So with those dashed lines you see at the bottom, that's what we're trying to break. That's where we're trying to break it. And then we use all of our different equipment to simulate the temperature, the conditions, and all of that. And that allows you to actually replicate what is happening in the ice. So you start off with something like this. In the best case scenario, you end up with something like this, where your central block has moved. So you have two places where your fiber is breaking, or your entire sample can break depending on the conditions. So what I want to do next is show you what it sounds like when you have ice at 100 Kelvin that is cracking. So what does it sound like? And this is sort of like the sounds that you'll keep hearing if you're on a mission. So if you have landed on the surface of Europa, this is what you're sort of going to get. So for very slow events, you get like a small creak every once in a while, sort of like if you're on your bed and your bed moves a little bit. For faster earthquake, so all of that sound is it cracking at a very high speed. So all of the ice is breaking up around your fiber. And then at the coldest conditions and the fastest conditions, so yeah, so that's just what it would be like. So imagine you're on the surface of Europa and you start hearing that stuff. So you know there's an ice quake or an earthquake that is going to happen. And so we are recreating all of that in the lab. And we're seeing like under what conditions can your fiber survive? Like if it's the warm conditions, then we find that it's actually the fiber cuts through the ice. So you can see the central block here, and it's cutting through the ice, so the fiber survives, same as here on Earth. But if it's like very cold conditions at 100 Kelvin, like minus 200 or minus 170, then you see that some fibers break while others do not. And that helps us find out what is a fiber we can actually use for space missions. And just this is an example of a microscope image of how these like completely shatter. What we also do is uh, use samples of different chemistries. So we make ice with sulfuric acid in it, ice with salt in it, and we freeze these fibers inside. And we leave them at minus 200 or minus 173 Celsius for 9 months to a year. And this is an example of a graph which we use to communicate our results. So on the right, on the bottom axis, you have the number of days, which is a little more than 8 months. And on the top, you have the amount of loss you're getting in the signal. And so by that, we can see how the signal changes with time at this. So it is recreating what a mission would be like. So if your sample is frozen in, or your tether is frozen in a mission on Europa for 9 months, then this is what it would look like. And we want to see what the sample signal is like. And then finally, we do other tests. We try to pull the ice, fiber out of the ice. We try to stretch it, and we do a lot of different stuff just to get a sense of like how can it break. And that is just like part of the work that goes into developing it. With the end goal being, we started building a new fiber that can work for space missions. So it is designed specifically to survive Europa conditions. But the issue is that right now it's too heavy. We can't fly it out because it'll take too much weight. So right now that is what we're doing is we're trying to develop it so it can become lighter and then we can take it out into the field. So that is pretty much sort of like a overview of the different sort of projects that we do and like how we design a mission. Like I said, this is just the first stage. This is how we design fibers and probes. The next stage is actually like proposing the mission and getting funded. Then you think about how to actually send the mission to Europa. And what I want to leave you with is what I'd mentioned I would do. Like, why should we fund planetary science when you can when there are hungry people here on Earth? So there's 5 different components that I just want to mention briefly. So the first is innovation. So a lot of the new things that we ever get in our developments, be it new aircrafts, be it new components, that all of that sort of stems from the research that goes into planetary science. Planetary science is not just sending missions to the moon or to different work. It's a lot of people, like tens of thousands of people working on solving a single problem. And to solve that problem, you have to think of and design new components and new equipment that allows you to have application not just in space, but everywhere else in life. So, like the first Apollo missions were sent with computers that had the same power or less power than your phone. Now we have incredible mobile phones, incredible computers, and all of that is sort of like the like trickle down effect from the amount of work and research that goes into developing these things. The second component I talk about is inspiration, which I hope some of you get from what I'm talking about today. Is like this world of planetary science is fascinating, and if more people get involved in the sort of research that is being done, be it engineering, be it science, be it arts, like if you get fascinated by it and you want to make a painting of Europa, then that is something that improves not just like what we bring to the world, but also our quality of life. And talking about quality of life, one of the examples I wanted to give is every day we use GPS. We use Google Maps to go places and look at things. We use Velcro straps on zippers and everything to seal it together. All of that came from research that was done for NASA. Like GPS was used for security and military purposes by America for their own missions, much before it was actually ever released to us. So all of that comes from the research that has already been done, and who knows what they already have today, which in 10 years from now is going to change how we do things. The fourth component is political partnerships, which we don't necessarily care about, but I wanted to point out the person in the middle of that image. Does anyone know who that is? Yeah, so Bakshi, that's Rakesh Sharma. So that's the only Indian citizen, like natural Indian citizen, who has actually flown to space. We have Kalpana Chawla, we have a whole lot of other Indian Americans who have flown, but like our partnerships with, in this case, Russia, and like that has extended beyond like any wars that happen here on Earth. So because if you're on the International Space Station or out in space, It does not matter if you're Russian or American or Indian or Chinese. They try to work together with each other. And that is sort of like overcomes all of the religion and the politics and everything that comes with. And the final thing is jobs. I love having my job, and there's a lot of people in India, like with all of the research that was done for Chandrayaan. So there's like tens of thousands of people working on very small things, and all of those get jobs and boost to the economy because of planetary science. So you have millions and millions of stuff that is being spent on that. But if you compare the amount of money spent for planetary science to the amount of money spent for military spending, it's not even comparable. We spend much more on building arms and bombs than we spend going and exploring space. And I actually wanted to end by playing a video from 1962 by John F. Kennedy, where he actually talked about why should we explore the moon. This was when they were trying to convince people that we should go explore the moon. And 7 years after their speech, they won the space race and actually got to the moon. So I'm just going to play that.
We shall send to the moon, 240,000 miles away, a giant rocket more than 300 feet tall on an untried mission to an unknown celestial body, and then return it safely to Earth. But why, some say, the moon? Why choose this as our goal? And they may well ask, why climb the highest mountain? Why 35 years ago fly the Atlantic? We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone. And therefore, as we set sail, we ask God's blessing on the most hazardous and dangerous and greatest adventure on which man has ever embarked.
And we are now actually going back to the moon. So we have the Chandrayaan, and now, like the Apollo missions, NASA has an Artemis mission. So the goal is in the next decade to send humans back to the moon. And again, this is something that is of interest to ISRO as well. And so at some point, we're going to go back to the moon. And like I said, think about colonizing it and setting up space stations and exploring further. I thank you for your time. I can take any more questions that you have, and hope you enjoyed it.
Right, that was great. I have always had an interest to learn more about your research. So after your PhD presentation today, I was the day when I got to see it in in its entirety. So I definitely learned a lot. So
Thank you.
yeah, so I have categorized few of the questions that have come in so far. Right.
Okay.
So I think first question that I have is, are you working on the Europa Clipper project?
So I was involved in the science team as an affiliate for approximately 1.5, 2 years, but I am a foreign national right now. So once my involvement with JPL ended, I could not continue working on any of that. So you have to be a citizen, or you have to have someone like a sponsor that allows you to work on it. So right now I'm not involved in it, but I was involved in it 3 years ago. Bakshi? Hello.
He's joining. One moment, please.
Okay. Sure. Yeah.
Shubham, you're in mute.
Yeah, I can, in the meantime, I can answer a couple of questions if that works. So I see a question that says, can we use your sketch or skeleton of your project? Yeah, I mean, go ahead, like give some credit, just like mention that where you got it from. But yeah, please go ahead and use whatever you want from the presentation. And like I said, I'll send some links and slides to it, so that should be useful. There's a question about, can we 3D print on the moon or Mars? Maybe. Right now, we don't have any 3D printers on the moon or Mars, but if we send a spacecraft, I think like if it has evolved enough that you can actually use it, like we'll have power sources, the same way we power our missions. So maybe it might be a good idea. And I think they will eventually be something like 3D printers to create something like our habitat, but not right now. Cosmonaut is a Russian scientist. But yeah, go ahead, Bakshi.
Yeah, I've answered a few of the questions which were direct. So there are a few questions that I did not know the answer to. For example, what exactly is a spectroscopy lab?
So spectroscopy is a technique. So, like I said, we are studying how light is reflected off of the surface of any material, planetary material, and then collected back. So spectroscopy is that technique of studying that light that is reflected back against the different wavelengths of it. So we've learned about the electromagnetic spectrum in school. So similarly, on the electromagnetic spectrum, how is the light reflected back at different ones? What is the intensity of that light? And that tells us which material exists. So a spectroscopy lab is just a lab which uses the technique of spectroscopy to study these materials.
Right. Okay. And there was one question asking what are Galilean moons?
So Galilean moons are just like the moons that Galileo discovered. So those are Europa, Io, Callisto, and Ganymede. These are the four major moons of Jupiter. So like much the largest ones and be the most fascinating ones for some people. But so those are just like they just named him after him because he discovered it.
Okay. So there were a few questions about our solar system. So, for example, what role does the Kuiper belt objects play in our understanding of the solar system?
Yes, so Kuiper belt objects are sort of like similar to, like I mentioned, there was this disk of material, right, that existed before everything else started forming, and then it started getting together and accreting and becoming these rocks. So Kuiper belt objects, they think, are the leftovers. Like everything else formed together, and then some of this stuff, it did not get stuck to anything, and it's just there in the middle of space. So if you study that, then you get to study what the solar system was like before planets formed. So they call them planetismals. So you get to like go back in time and study what the universe was like at the beginning, or like the solar system was like at the beginning. So they're like very fascinating, and lots of people like there are missions to that as well.
And so, what are the modern satellites trying to collect from the sun? There was one more question.
So modern satellites are mostly looking at the intent. So again, there's a lot of stuff, and like I mentioned early on, like my PhD is in planetary science, but not in heliophysics. So heliophysics and those are more looking at the sun, but I do have a general understanding of it. So like I said, not my specialty, but so some of the missions are looking at the intensity of the particles coming from the sun. So they call it like solar plasma. So sun also is not like a regular surface that stays the same. If you look at videos on YouTube, you'll see sort of like the lava-like structures. So there's something that's coming out from the sun, something going out, and that solar that change in the sun changes the particle intensity and the radiation, and that can have effects on like our antennas here on earth, the electronics, the magnetic field. So like the devices we on our phones, all of that can change. So if there's like something that's very strong, then there's possibility that like the power grid goes out, so you don't have any electricity. So people, and those are like worst case scenario, that's probably not going to happen, but so people want to see what actually is happening with the sun. How is it changing? What is its intensity? All of that stuff. So, and that's just like one part of it. I don't know a lot about the sun.
All right, all right. So there was one question about Jupiter. So I think you touched upon this topic while the shape of the moon was asked, but someone is asking how does Jupiter maintain a spherical shape despite being predominantly composed of gas?
Yeah, so initially there was some rock inside of it, Jupiter as well. And if you looked at the solar system image I showed, the scale of Jupiter is so massive. It's like 70, 80 times Earth, or like even more than that. I don't even remember. But because it's so massive, even though it's a lot of gas, but combined, it's like the mass of it is strong enough that it can have a good gravity. So it's again like GMM by R square, that equation of gravitational acceleration and attraction. Like it's all again Newton. So everything, the answer is gravity. It's like it's massive enough that it just pulls everything and maintains it. And it also keeps the moons in check around it as well, in orbit.
Okay. So we have a few questions about the Earth and the Moon.
Mm-hmm.
So first question was that I found really interesting is can Earth have a ring?
So Earth does not have a ring right now because again, gravity. So it was so massive and so strong that it cleared its ring around it. So why does a ring form when your gravity is not enough to pull all of the fine particles? Or if there's like some sort of like in the case of Saturn or Enceladus, you're like ejecting particles. So you have some ice that is coming out like a geyser or a plume. So geyser plume is the same thing in this case. So it's coming out and it's like depositing around it and it's not strong enough to be pulled back down to the surface. So that creates your ring because you have a source of particles that is not strong enough to be pulled out. In Earth, the gravity is so strong that anything that may be ejected out, it just like immediately falls down. Like our lavas are not like having massive kilometer high explosions. So it's like it gets rid of a ring. So we don't have it.
So did Earth have a ring in the past, like when it was being formed?
Yeah, initially, like I said in that video, there's like something like a disk of sorts, so it starts forming quickly. So maybe for a little bit of time it might have had a ring, but I think like very quickly in the formation, like, and I saw a question about how old it is. So it's like 4.57 billion years, and the moon was formed within like the first few million, 100 millions of years. So like 4.53 billion for the moon. So like very early in our solar system.
Right, right. Someone had asked even where are Earth and
Yeah,
Moon born. So yeah.
yeah, yeah.
There was one question about the color of our moon. So is there any, is it white like we see it?
No, I mean it's not white. Like we don't see it white. It's like gray or dark gray. I
Yeah.
think. Like, so the thing is, so it does not have an atmosphere around it, like a very thin atmosphere. It is an atmosphere, but very thin, and it's mostly like basalt and a little bit of granite. So like we have basalt here on Earth, so it's not necessarily like it's mostly grayish, I would say.
Okay.
But yeah, like you can look up like a lot of the stuff, like you just go on NASA's website or you look up on Google, then you'll see what is basalt made of. Like so it's like different individual materials, and that's where the geology component comes in.
All right. So there were a few questions about the Big Bang and the universe. So
Yeah.
I'll just ask them out. So I'll
Uh,
read all the three questions that were there in this journal. So
uh-huh.
one was Big Bang is the starting point of the universe. So where was it created and how did it look like when it was evolving? That was question number
Okay.
one.
Uh-huh.
Second was could there be an edge of the universe? Can it be seen with the naked eye? And third
Mm.
was how much area exactly is the universe occupying?
Okay, so I'll answer the second and third ones first. So I don't know if there's an edge. No one knows if there's an edge. We have tried to send, like, to our solar system itself, we have tried to send missions from the 1960s. That was the Voyager missions, and it just left our solar system after 70 years. So we have no idea what's actually out there. We think like the universe might be expanding slowly over time, but yeah, it's like the universe was created around 8 billion years before our solar system was created. And our solar system is just one in like millions of solar systems. Like again, you can look this up. There's a James Webb Space Telescope, which is taking images of the universe. from like it's outside Earth. It's a satellite that just got launched, and so you can look at images, and each single speck that you see is a solar system. Sorry. So I have no idea how big the solar system is, and like it's massive. Uh, and so you cannot see the edge with naked eyes or even with any telescopes that we currently have right now here on Earth or in space. For the Big Bang, so if you remember the video that I played about how our solar system evolved, so the idea is that Big Bang started from this one small, infinitely dense point, and then it just expanded from there. So, like the best, we have no idea again what that looks like. That animation of our beginning of our solar system that can sort of give you an idea of like how there's a sudden expansion, and you have all of this material that is being expanded, and so you get these rocks, these ices, these grains, these gases. And so something similar to that, but on a larger scale, where like everything was created instantaneous. And again, this is a theory, and it's astrophysics, which again is not my specialty. So I'm going to say I don't know perfectly well.
Okay, so there is one person who's asking, I think I saw this question a few times. What is ICE 7? Is there any specific ICE called ICE 7?
Yes. Oh, yeah. So it's like you don't want to get into that at this stage. It's like ice has, like, depending on how ice forms, like I'd mentioned, there's amorphous ice, there's crystalline ice, and then there's like tens of different types of ices based on the pressure conditions under which it forms, the exact temperature under which it forms, its crystal structure. So ice 7 is another type of ice. Ice 4 is a different type of ice. Even crystalline ice has like hexagonal ice and cubic ice. So these are like really getting into details. If you're interested about it, this is great. Like there's like research papers that talk about it that are like open access, so anyone can view it. You don't need a university account or anything. But yeah, just go look at it, and if you're interested, there's a lot of information about it out there. But yeah, this is like actual like PhD like research. So like people spend their 5 years looking at ice properties.
Right. So I think we'll take one more question and then we'll close the session. I'll give an option to the students to send in more questions through the feedback form and other means so that we can
Yep.
answer these questions later. So there is one question which said, back in time, the Earth was too covered with ice, but it got changed over time and got covered with an atmosphere as well. Why
hmm
do other planets not have this kind of a climate change? Is
So because it's too far, at least that's my understanding. So the sun is not strong enough. So you don't have like something, and there's not like any most of the gases like here on Earth, like you have oxygen, you have carbon dioxide, you have nitrogen. So a lot of these in the outer solar system, like they exist as ices. So you don't have like that gas form around it, and you don't have something like carbon dioxide around it to have a greenhouse effect. So there's nothing trapping the sun, which in itself is so weak that far away that you don't get like that same amount of atmosphere yet. Who knows, like in how as the sun evolves, maybe it'll get better, maybe it'll get worse, but they don't have anything, and they've been like around for 4.5 billion years as well. So
understood? Okay. Okay. I think, yeah. So I think there will be a lot of questions.
uh-huh.
The, there was one question right now asking about what will happen if you landed any satellite on Jupiter. Is that possible?
So Jupiter, you can. So yeah, there's definitely they want to explore it. So like you once you get through the gas, there is like rock underneath that gas, but because that gas is so dense. So you can imagine the amount of pressure that will be on any satellite. So you can like technically land, but I don't know if we have any capabilities to survive those conditions. So sort of like more work like what I was describing for the robot, that sort of work would have to be done where you have intense pressure from top of the gases to see like you don't actually lose your signal or your spacecraft as soon as it enters like Jupiter's gases. So you can like they have looked at like Titan and other places which have like organics like on their surface and in their atmosphere, and like it landed and it died within like a few minutes. Like this was again in the 80s or something. So
So on that note, there was one more question. Are we still in contact with Voyager missions? Are we?
Yeah. So JPL has a deep space network. So there's like three different massive satellites across the world, and they operate one of those from JPL. So there's a control center of sorts. So it's like you can again look at these images online, and so they show each mission they are in contact with and when they are communicating with them on like a big display, which is like really good to see. And so yeah, they were in contact with I think Voyager.
Okay.
Voyager 2, I think. Yeah.
Not Voyager 1.
I don't remember about Voyager 1. Maybe. It was probably online.
Okay. So I think we are at the end of the session. Thanks a lot for coming in so early on a
Yeah.
Saturday. And thank you all the students and teachers, principals who have joined in right now for being a part of this webinar. So yeah, we'll be getting in touch with everybody who was a part of the webinar through a WhatsApp so that you can get to know. So Vishal has said that he'll share a few resources. We'll share that with everyone. And so there is a feedback form as well. Please fill that out and we'll be sending in the e-certificates for the webinar to people who put in their names and numbers over there. Right. So thank you, Vishal. Thanks for coming in today.
No, yeah, and thanks for joining all of you. It was great to talk to you. I hope some of you enjoyed the concept of planetary science and is something you might be interested in. So, yeah, hope to see more of you.
Thank you. Thanks a lot. Bye bye.
All right. Bye bye. Have a good night.
Yeah. Good night.